know, how to understand everything makes this more complicated. And you know, one of the lists of the things about the so-called many minds version was that there wasn't any conflict.
Right. But do you not take my point, right? That if you're talking about incompatibility between two physical theories, and you're telling people we've got these two physical theories that are incompatible with each other, not mentioning the Dirac equation, not mentioning the fact that these two theories are pillars of the Standard Model, that pretty much everyone in the physics community thinks that their worldview is a combination of like special relativity and quantum theory, right? That it's odd not to mention that fact.
An exaggeration in one direction doesn't require an exaggeration in the other direction.
Okay, fair enough. Yeah, so, okay. I mean, what's my exaggeration? I mean, I just had a negative lesson, which was that it's not correct to say there's absolute distance, and it's not.
This is completely wrong.
What I said?
No, yeah, what you said that David said.
Oh, it was completely wrong. Okay, sorry.
You can imagine a more sympathetic reading of all of that. Anyway, it's not my job to David or
No, okay. Yeah, I guess I can be more sympathetic. So it's not that what he said is completely wrong. It's that it was like insufficiently nuanced and in some ways misleading. But I mean, there's this tradition of saying that quantum mechanics is non-local, and what I wanted to say was that's not the right lessons to learn, right? We shouldn't learn that lesson. We shouldn't think that this is non-locality in the classic sense of what that means, which is something like action at distance, or causal processes across space-time with nothing happening in between, or whatever. I mean, people continue to talk.
It's not as though anybody said that it was like that.
Well, I mean, punches and black eyes is a causal process, right? It's supposed to be analogous, and I'm not, what I'm saying is...
That's why I said I think you were taking that too seriously. That was the grab one in. I don't think the implication was, and like punches, your fist has to reach across. It was rather something like, it would be as if a punch in one place, without there being anything going on in between, had made a black eye in Cleveland.
Right, yeah, okay. But what I think you said is wrong. It's not as if that at all. That's not what it's like.
Well, in some ways it is.
But in like many important respects, it's not like that at all. Because punches cause black eyes don't cause punches. And if you tell someone that there's a punch, there's a black eye, everyone immediately sees a causal arrow from one to the other. It's not like that's a kind of extraneous feature of the situation.
Black eyes do those punches.
Sorry?
That would be a reason.
Yeah, okay, so look, I'll concede that I could have been more sympathetic, and that there's an important truth to the fact that theories that posit counterfactual definiteness can't recover violation of Bell inequalities locally. But I stand by the lesson I was trying to get across, which is this case motivates another category of dependence that isn't causal dependence.
There's this famous article by Brian Stearns, basically that's the lesson of the article. In some ways it's like causation, some ways it's not.
Right.
He has a big list of
ways in which is like one or the other. Okay, fair enough. Okay, so your final version of your question is, insofar as you said anything true, you just said what Stearns said in this famous article. Okay. David.
I mean, this is related to various points in different angle. I mean, isn't the right thing to say about the various examples like theoretic equation and flow that these are all examples of unitary quantum mechanics? The unitary type of quantum mechanics stands in beautiful coherence and special relativity.
Right.
The unitary type of quantum mechanics has probability flow that's smooth and very nice differential equations which have high dynamic analogies. But if you're David, and if you're basically anyone who's studied Atlantic philosophy, then you don't think the unmodified unitary quantum mechanics is an empirical theory. You think it predicts a whole bunch of things like Maxwell's superposition, but you don't see around this.
Right.
And so, insofar as quantum mechanics, without entails or something predicted to David, it has to mean quantum mechanics whose dynamics is the kind of Dirac-von-Neumann unitary dynamics punctuated by wave function collapse. And wave function collapse is not Lorentz covariant. And wave function collapse is fairly, possibly realist wave functions action at distance in a relatively straightforward sense. And wave function collapse violates that continuity equation you were putting up there. And, I mean, if you like, that's mystery. It's profoundly mysterious that we have theory, a great part of which is beautifully coherent with locality and special relativity, and another crucial part of it isn't. The shame can't find somewhere reconciling that, but absolutely.
There was only so many yeah, I totally agree. Look, I'm not trying to say that there isn't any mystery to quantum mechanics or anything. I mean, all I was trying to do is say, like, I find it odd that people don't draw attention to that continuity equation when they talk about non-locality and quantum mechanics, because there's an equation that demonstrates the extent to which unitary quantum mechanics is local.
But it's an equation that's violated in wave function collapse.
Sure.
Which is the context. It's violated in the measurement context, which is the context in which these phenomena, these action distance phenomena are supposed to be occurring.
Yeah. Okay. Fair enough. So.
I mean, it's violated in the sense that if you regard rho as just being a function of psi, if you want to be unlimited about psi, you'll have to get complicated.
Yeah, I mean, I'm not sure that I want to be a realist about psi, and I'm one of these people who thinks that, if you really held a gun to my head and said, like, Bohm, GRW, Everett, or some kind of neo-Copenhagen type view, then I'd go for the neo-Copenhagen, some version of Copenhagen, probably, right? So
with collapse.
No, because I think Bohr never talked about collapse. He didn't think that wave functions were things in themselves, right? So, sorry?
The way it got evolved by Neumann.
The way it got evolved by Pauli, yeah. But then that seems like, that's just a silly theory, right? To have like this realist theory of wave functions and then think collapse is a real physical event, right? I don't want to go that way at all.
The then theory, to be fair to David, a premise here is that we have to have a clear realistic account and not passive Justerianism. And the worry about something like neo-Copenhagen is that it has passive Justerianism. We know that the Kirchner's thing of a probability in any remotely straightforward sense runs into a terrifyingly spiky thicket of negotherms. And so what we have in mind here becomes extremely obscure.
Yeah, okay, so what I don't buy is necessarily that we need to have a realist theory in that sense, I suppose. But look, I mean, there's one other thing I was going to say. Oh yeah, look, here's something else that I think that people say, David says, that I think's not right. It's the flip side of what you said. So, one thing he says is that quantum mechanics with collapse isn't empirically adequate because it says there's macroscopic superpositions, but he doesn't think we see them. Without collapse, sorry. But here's another thing he says. He says that quantum mechanics without collapse doesn't have any empirical consequences at all, right? So, and about that, I think, no, look, that's misleading as well, right? There's whole programs in physics and quantum chemistry and so on that get empirical content out of quantum mechanics without having anything to say about theory of measurement or collapse or anything else.
All those theories make use of Born rule to get that fixed outset. So if you think that the only way to understand Born rule in the context of realist theory is that it's an dynamic collapse process.
Right, but if you just take the theory of electronic orbits, of quantized energy levels, there's so much.
All of those things ultimately make empirical contact by probabilistic predictions. The probabilistic prediction is very heavy if you can have one, but.
Okay, well. is that really true? I mean, take the something like the BCS theory of superconductivity. Does that use the Born rule and collapse?
Well, it uses the Born rule, and if you think the Born rule only makes sense in realism, it's true. I have to say that. Again, you find that, but it does use the Born rule.
Okay.
Obviously, if you're not going to deal with the loss-way amplitude rule, then you don't have any route to get content out.
Which you really think you do?
Okay.
Yeah, but you have to.
Okay. Well, gentlemen.
Yeah, so that's interesting, the preliminary remarks. So just quick clarification question. So you said there's a problem of weighing the virtues when we're doing metaphysical theorizing and engaging
Right.
in metaphysical inquiry. Is there a similar problem of weighing the virtues when we're engaged in physical scientific inquiry, or do you think that in those cases, the kind of reasoning employed there just gets boiled down to probabilistic reasoning?
Oh, okay. So one story about that is that that philosophers have given too much weight to the role of theoretical virtues as decisive in solving the undetermination problem, so Duane's line on this is that the theoretical virtues are only ever used as a heuristic, as a stopgap, until you can get more empirical predictions and choose between the theories on that basis, ultimately. So you might defend the use of theoretical virtues as methodological and heuristic, but not think it's really epistemic, not think it really settles the matter, right? You might think, look, the best bet I can make about which of two rival theories that are currently empirically equivalent is going to be based on theoretical virtues. But what's really decisive is which one of them ends up being empirically equivalent when it's further developed. And so I'm kind of tempted by that line, right, that philosophers have overemphasized the role of inference to best explanation and theoretical virtues in
Solving underdetermination.
yeah.
So just a more substantive worry. So I actually think that metaphysical theorizing can help with problems of underdetermination in physics and in science. So here's an example I wanted to float and see if you can knock it down, right? So I have a drastic example and then a less drastic example. Let me start with the less drastic example first. So in metaphysics, you got this debate, these debates in philosophy of time concerning whether or not presentism is true, right? And so some people think that they've got evidence for presentism, but isn't necessarily the kind of evidence that issues forth from physics. They might say something like this: look, it's crucial to presentism that there be such a thing as temporal becoming, right? And so some people have argued, Adolf Greenbaum and others, that temporal becoming sort of has no real place in, final in-game fundamental physical theorizing. But some presentists maintain that there is a kind of evidence in our experience, our everyday experience, the phenomenology of our experience, for the existence of temporal becoming. Now, this, of course, wouldn't establish that presentism is true, but it seems to provide at least one leg and a number of legs you would need to support the conclusion that is, the thesis that presentism is true. But let's just suppose that you could support the conclusion that presentism is true with similar kinds of moves like that, right? That doesn't resort to physical theorizing, but was a kind of purely metaphysical theorizing. So what I want to float is this, right? If presentism is true, then you're not going to want to affirm particular interpretations of the special theory of relativity, because you're going to need, it seems, absolute simultaneity. So it looks as if, given proper support for presentism in metaphysical theorizing, you're going to have a solution to the problem of underdetermination with respect to the interpretations of STR. You might think the Lorentzian interpretation is empirically equivalent to the Minkowski interpretation, and there's a real problem of underdetermination. What's going to win out? Well, I've got these arguments for presentism that my epistemology says are knowledge conducive, and this is going to force my hand into choosing the Lorentzian interpretation over the Minkowski. So I just
Is this supposed to be the less drastic version?
Sorry.
Is this supposed to be the less drastic version?
There's another example that's even more drastic, I guess, if you want to put it that way. Anyways,
okay.
I don't think it's that crazy. The idea is just, look, there are other ways of supporting and motivating metaphysical theories than by appealing to the physical sciences. I'm all for reading off to some extent your metaphysics from physics. I'm cool with that. But there are other ways of securing justification.
I mean, I suppose what I'd say is it sounds to me like you were just appealing to empirical evidence. If you were saying there was empirical evidence from, that presentism was true.
Oh, right,
It
from
didn't sound
phenomenology of experience.
Yeah, so that just sounded like, I mean, we could argue about that, but it didn't sound like you were appealing to metaphysical reasons, but just other empirical reasons, like you think there's empirical evidence that presentism is right.
What I meant by the evidence isn't physical, it's just that this isn't the kind of evidence you're going to read off from like physics, like physical theories. This is just evidence provided to you in the phenomenology of your everyday experience as an agent, as a cognitive.
Okay.
That's all.
Yeah.
And the idea that
I don't think, I mean, what I think you have evidence of is that there's temporal becoming in your experience.
Right.
But there's all sorts of stuff in my experience that isn't there in the world, so...
And there are arguments for the thesis that the temporal becoming is objective and not merely subjective and dependent upon the cognitive activity of the experiencer. There are arguments like this out there in the literature, and I'm just suggesting
sure.
that this is a way that you could do metaphysics, and that way of doing metaphysics could inform what's going on in your physical theorizing, that's all. Doesn't seem correct.
Yeah, I mean, if I said anything more, I would just be talking about that specific case of presentism, which may be a bit off the topic. I mean, I don't think I even understand presentism actually, and don't think that it's the same thing as temporal becoming, because I think you could be an eternalist and also believe in temporal becoming.
Right, and that's why I said this would just be one leg in the supports for the thesis that presentism is true. And I know that presentism, of course, is not the subject of the talk. I'm just saying that this seems to me to be a way that metaphysics could inform physics, and this seems to be drastically opposed to, well, your preliminary remarks about metaphysics and physics.
Okay, sure. Okay.
May I ask you to tell us more about weak values?
Oh, yeah. Yeah, sure. Okay, so quick tutorial on weak values then. Okay. So, so two things I'd like to know. One is that there's such thing as weak measurement, you've probably heard of. You can only weakly measure weak values, but not all weak measurements are of weak values. So, weak values only show up using weak measurement. That's one. Second thing, weak values only show up with post-selection. Okay? So here's a really crude version of it. If you take spin, then if you have n spins, then you can weakly measure them with an accuracy root n. So weak measurement of a single spin is completely useless. But if you have a spin million system, now root n is pretty small compared to n, and so weak measurement is informative. Okay, so weak measurement doesn't change it doesn't violate the uncertainty relations. It doesn't obey. You can weakly measure position and then weakly measure momentum and then weakly measure position. Well, actually, no. If you make more than one weak measurement, it turns it into a strong measurement. So you can't cheat by doing lots of little weak measurements. If you do that, it counts as a strong measurement. But you can certainly, if I weakly measure position, then weakly measure momentum, that's no problem. So now think about the following fact. Post-selection in general changes your probability distribution for intermediate measurements. That's kind of trivial. So if I have a state preparation of spin x is +1, and now you ask what's the probability of spin z being +1 in the middle here, like how likely is that? You're going to give probability a half. But if I tell you that we're only considering those parts of the ensemble which at the end of the whole procedure were found to be spin z being +1, and if the Hamiltonian is 0, then you now know that all of these were +1, right? So clearly post-selection changes the probability of diffusion of intermediary measurements. Okay, there's nothing interesting about that in a way, right? If I had a load of kids and I had the probability of them doing well at high school, and I post-selected the ones who later got a really good degree, it would change the probability that they did well at high school, right? But it wouldn't be because they're getting a good degree, like, did anything. It would just be like, I'm refining the probabilistic information I have. Okay, but now it gets more interesting when you consider a weak measurement of something in the middle here rather than a strong one. So if you imagine measuring spin 45, which is defined to be spin x plus spin z over root 2, and you weakly measure that, then naively you kind of think, imagine running this kind of heuristic, right? You think, well look, these particles here, they're all up in x, and they're all up in z. So let's just suppose that we put those values in here, then we're going to get that 1 plus 1 is 2, and 2 divided by root 2 is root 2. So we're going to sort of imagine that their value for spin 45 would be root 2. Right? That's completely crazy, because root 2 is bigger than 1, and 1's the biggest value that we could have for the spin. Right? But actually, if you measure this weakly, then what happens is this. If I take my initial ensemble that are all up in x, and now I look at all the measurement results for the weak measurement of spin 45, I'm going to get a bimodal distribution, which is mostly around, which is more around 1 than around -1. But weak measurement is when, roughly speaking, the width of the Gaussian, I mean, it doesn't have to be a Gaussian, but suppose I've got a measuring device which gives you a Gaussian distribution of point of position, right? There's always going to be the coupling of the system to the measuring device is always going to be not perfect, and weak measurement exploits the imperfection in the measurement to allow you to do non-disturbing measurements. And the way it's allowed to do that is the width of the Gaussian is wider than the gap between the eigenvalues. So you're sort of not narrowing things down enough to disturb it. And so when I plot when I take that distribution, and I've got this bimodal distribution, and they're both down, then there's going to be some parts of the distribution that go away from 1 over to root 2 because of the error in the device intuitively, right? But now the really interesting thing is if I take the sub-ensemble that I get by having spin z equals +1 at the end, so I post-select, then I've got this nice distribution, and I've got it all, it's kind of like something like this, and here's root 2, and now I take away everything that isn't up in z at the end, and I find that I have a little Gaussian centered around root 2. Which, now this is really strange, right? So the thing to realize about this is that the number of things that I have to throw away is absolutely vast, because this is a distribution based on many measurements of n spins, and I'm only going to keep the value where all n are +1, right? Now if I said n a million, then clearly like the proportion of those final measurements where they all come out up. I mean, there's two ways to have n spins. I either have a spin n system, or I have n copies of one spin system, right? Now, either way, like, it's very, very unlikely that I'll get all n being up. And so I'm throwing away masses and masses and masses of data, just like that. But nonetheless, when I do that, I find this little peak around root 2. And interestingly enough, the width of this Gaussian is exactly the same. Like the standard deviation is just that of the sensitivity of the measuring device. Now, what makes this really interesting is I could do weak measurements of position. And in particular, I could have a superposition of particles in a particle being in different boxes. And now my weak measurement of position, well, how could I do that? Well, suppose it's a charged particle. I could weakly measure the position in more than one way. I could weakly measure it by weighing the boxes or something, like have some kind of gravitational probe, or I could weakly measure it electromagnetically. And both of those ways of weakly measuring will tell me that the particle is in the box, if indeed, the theory tells you that you're going to get. Going into this too quickly, but you can have states where you've got an initial state which is A plus B plus C, and a final state that you post-select for, which is A plus B minus C. And on those ensembles, weak measurement is guaranteed to tell you that the particle is guaranteed to be positive for these two boxes and not for this one. But even worse, you'll actually get a minus one eigenvalue for it being in this box. In other words, if you used an electromagnetic probe, it would be repulsed as if there was a particle of the opposite charge in that box. And the thing that's interesting is that logically independent ways of probing weakly will both tell you that the thing's there or not there. And so if you have some kind of like reality criterion, like, I think the table's real because unlike rainbows, rainbows I can see them, but if I use different sensory modality, I don't get anything there. But with a table, I can see it, I can bump into it, I can smell it, I can hear it, And so, like, you might think, well, I've got to give some reality to this weak value because logically and physically independent ways of probing the weak value kind of converge on seeing that. But unfortunately, that requires a counterfactual kind of judgment because I can't do more than one of those logically independent ways on the same system because that would turn it into a strong measurement. I'd be measuring more than once the same thing. So then the question is the weak value that I see when I only look at the sub-ensemble that I get by post-selecting, is that a trace, is that weak value kind of ontological dependence on what happens here based on what happens later? You can't think it's the other way around because the probability, if I look at the whole ensemble and I look at the values that have the weak value, it doesn't change my probability of the later measurement result being up. So the observation of the weak value gives you no increased probability of finding the post-selected strong value later. So the conditional probability of the later up measurement given the weak value is the same as just the probability of the later up measurement. But the conditional probability of finding the weak value for those ones that are later up is 1. So it looks like there's a counterfactual, there's a kind of modal dependence of this on this, but I can't use this as a predictor of that. I can't think there's a common, like there's a kind of hidden variable state here which causes this later thing. So one thought, one thing that some people say, like Hugh Price wants to say is, well, this is just a retrocausality, that's what's going on. And he, of course, says the same thing about EPR. He just says, well, that's the way to solve the problem, right? It goes back down the light, back up again, and it's all local, no problem. But if you had reasons for thinking that this is disanalogous to causation, then you might want to say, right, well, it's not causation from the future to the past as such, but as some kind of non-separability of the past and the future, or some kind. And so this is in my thought. I mean, this is really, really hazy, right? But I want to say, just as the connection between the two wings of the EPR experiment there seems to be an ontological dependence without causation. And just as there seems to be like not action at a distance in the AB effect, but some kind of non-separability, and I think, well, maybe this is another case where we have this extra category right? Some kind of ontological dependence without causation. But really very speculative. I mean, I'm just floating that and saying, and sort of advertising it and saying people should like find out about this and think about it.
So I wanted to invite you to expand a little more on this idea of ontological dependence without causation between the two wings of the economic experiment. Perhaps, I have to confess I didn't understand what you're saying with the values. But it seems like, just to take the two wings of the EPR experiment, and you want to say there's some ontological dependence here. So like that, there are several different models still of how we should think about this ontological dependence. One is that we have this labeled as A and B, is we have some kind of symmetrical dependence where A is ontologically dependent on B, and B is likewise ontologically dependent on A. And that seems problematic, at least insofar as it's standardly thought that ontological dependence is asymmetric, and moreover, it seems a bit odd, I mean, to the extent that upon which A and B are codependent. And there's even ways of doing it where you don't have grounding at a distance, where you have what A and B are codependent on being something big that encompasses both, just for their fusion. But A and B will be enough to sort of, so you see that A and B are each dependent on A, the mere algebra sum of A and B. That would be a different ontological dependence model. I was wondering if you had a specific model of how the
No, I don't at all. But except that I do think that ontological dependence can be symmetric. So I know that people standardly say that it's asymmetric, but I'm persuaded by examination of other cases in physics that make one think that it might be symmetric. So Kerry Mackenzie has this analysis of the dependence between group structure and particles, and actually originally motivated by her arguing against me and Steve French, who seemed to say that particles depend on group structure, and group structure is the primary, most fundamental thing. And she says, no, that's wrong, it's symmetric dependence. So insofar as you bought that example, and maybe others, you might think, no, actually I don't have a problem with symmetric dependence. So I don't have a model of ontological dependence, but I think the whole thing I think about the EPR case is that it's symmetric. That's why I don't like thinking of it as causal. Because I think causation isn't symmetric, this relation, whatever it is symmetric, so it's not causal. So it's got to be some other category, right? And so
at least in this case, I don't know what to say about the particles versus group theory case. There is an alternative interpretation of how the ontological dependence runs, this kind of common ground story that I was telling. That would at least preserve the asymmetry of ontological dependence in this case.
But I don't have anything to rule that out particularly. I mean, but I think these are interesting cases worth thinking about. As I said, I really like this building a paper on taking a throwaway remark of David Albert's too seriously and a load of speculative things about this text. Gordon, do you want to say something?
Oh, well, this is an optional question.
So what's its valence?
I'd be interested in hearing more about the Mackenzie thing that you just said something about, because I wasn't sure what the relata were on these in this relation of mutual ontological dependence. Group structure seems like a mathematical thing to me. Probably that's not the sense in which you intended it. So I just wanted you to tell me what. So here we have A and B; those are events, fine. In the case you have in mind, what kinds of things are the A and B?
I guess, this is like somehow rarefying group structure and saying, no, it's not a mathematical thing, it's a physical, it's the symmetry of this interaction.
So let's say that's A. So A is the symmetry of interaction, and what's B?
It's the multiplet of particles.
So that's like a structured family of natural kinds or something? Is that the...
I guess. right? And the idea is that French and I said that the group structure comes first, and the particle ontologically depends on the group structure, and she says, no, that's wrong. You should think of these things as mutually dependent.
And is the test there just if one has been different, the other would have to be different? That's how we discover relations of dependence, in this case we find way in both directions.
Right, yeah. And then, so what's the other example of mutual ontological dependence other than the results of the 2 weeks of the EPR experiment? Because that's contentious in this context. I don't know. I have to remind myself about that. I think I'll see if I can remember an example. David.
And just coming back actually to the thought about the measurement problem and different theoretical virtues. I wonder if that quite characterises, at least inside philosophy, where the disagreements on the measurement problem lie. I mean, if you have, if you look at some physicists, and certainly I think people in the popular culture, and ask them what's wrong with Everett, they'll show you're dead right, they'll talk about ontological occupancy. And you'll see these kind of back and forths from Deutsch will say, well, no, you want to be cheap on assumptions, which depends on the universe system as well. But if you look inside the philosophy disagreement, then it seems to be much more that people are concerned that the Everett interpretation is either incoherent or empirically inadequate for a variety of reasons, but particularly because of probability. And you don't by and large find people, I can't think of anybody inside philosophy who would say, yes, I think the Everett interpretation is a viable possibility, it saves the phenomena, but for other extra-theoretical, extra-empirical reasons, we don't like it. I know lots of people who I think would, probably David, for instance, who would say, well, if only the Everett interpretation worked because it's got,
Right, so you think it's just incoherent, it's really an interpretation.
Yeah. And to a lesser extent, if you look on the other end of the Atlantic, if you talk to Neil Simon, why we don't like things like bone strategy, you'll find some carping and extra-empirical objections and things, but mostly you'll find a serious worry that it can't handle the intrinsic field theory case properly.
Right,
So
yeah.
you said that in some ways that there's more, in a sense that means the debate is more kind of deadlocked
Right, I mean, but you could sort of take that as grist to my mill, right? Because you could say that precisely because everyone can see that there's no progress to be made in this case by theoretical virtues, they're looking to other ways to solve the deadlock.
Well, I'm not sure that's right. I mean, you could say that you could argue it supports the kind of broadly almost temporary skeptic case that says we're not getting loops there, which is definitely here. But in the narrow case of extra-empirical virtue, I think it's that you get that kind of clash where you think here are multiple possibilities, none of which are just flatly ruled out by the data or by logical coherence, and I choose between them. But I don't think the pro-con Everett debate at least has that character. I mean, maybe among people. So I think a lot of people would say that we have to be real, can't be Everettian, but Bone and JW are viable ways of doing things, and maybe their dispute internally comes down to extra-empirical virtues.
Yeah.
But I don't think the
maybe that's right. I mean, I've always thought about it that way, though. I mean, I've always thought, well, if you're schooled in philosophy of science and the realism debate, and you've learned about all these you learn about the underdetermination problem, and you learn about theoretical virtues, then the natural thing to think when you're presented with the different interpretations of quantum mechanics is, oh right, well I better just think and see which ones have which theoretical virtues and try and solve the problem that way.
And I think that's actually
it's a fairly natural kind of.
Yeah, absolutely. And I think it actually often turns up in broader philosophy, and ironically, it turns up a lot in the broader philosophy of science context as an example of extra-theoretical virtues of view. It's quite hard to find these examples in physics proper, but you find them here.
But it's certainly true as well that in the early debates people said things like bone theory is ad hoc, so you shouldn't believe in it, and they're explicitly saying, that's a super-empirical device that we use to solve underdetermination problems, analogous to, why we shouldn't believe that the Earth is in fact 6,000 years old.
I think the case is better that way around, to be fair. I think people it's not that hard to find people in print who say, sure, the bone theory works, but it's unattractive for the following.
For the following super-empirical.
What you don't often find is the other way around. People who say, well, the Everett interpretation works, but it's unattractive for the following it can't make sense of probability, it has no coherent way of
Yeah, no, that's
describing
interesting. I mean, I suppose I'm perhaps over-influenced by you.
Talk to us too,
Because when I talk to you too long. So when I sort of teach my students, I end up, I put all the interpretations down and they say, okay, so how would you choose between them? And get people to think about theoretical virtues. But yeah, maybe that's because I'm over-influenced by you and think it's coherent in the first place.
that's an exercise.
Yeah.
But controversial.
Okay, yeah. Barrier.
So, this reminds me that I wanted to say before, the main metaphysical, story to tell about in history of interpretations of quantum mechanics is one thing we didn't really emphasize, I think, and that's that prior to the development of Bohmian views or their popularization and Everett and GRW, it was widely thought, and may still be widely thought, that it's impossible to understand quantum mechanics realistically. That there's no realist interpretation of quantum mechanics. The Steel Copenhagen information business, if you're, is a late version of that. And the lesson to be learned is that, in fact, that's not true. That there are realist interpretations of quantum mechanics.
Yeah. Okay. That's.
So this is on the line of relation between physics and metaphysics and what one can do for the other.
Okay.
The metaphysician can say to the physicist, try to be really clear about telling us what the world is like if your theory is true.
Yeah.
But to be fair, because all these theories came out of physics in the first case.
Yeah.
Yeah. I mean, I don't have a problem with that. I don't know if that's supposed to be intention for what I'm saying or not.
No, not as supplemental.
Yeah, fair enough. I mean, I actually think that metaphysics has a positive role to play in science, and I can think of a million examples of that. And and as I said, I'm interested in naturalized metaphysics, and I'm interested in the construction of a unified scientific worldview to drive science forward and so on. So, I'm not someone who thinks that metaphysical questions are meaningless and not worth pursuing, or that it's not worth trying to give interpretations of theories and you should be quietist about it or anything like that. No. I mean, in fact, this whole point of this was to try and draw a tentative metaphysical lesson that hasn't yet been drawn. Yeah. Jan, were you going to say something?
No.
Okay, that's a shame, because I thought you were looking vaguely sympathetic. I was hoping you might want to elaborate on that soon.
Well, I mean, a lot of what you said, I think about the symmetric dependence relation. I mean, those kind of stories that I told is exactly the right story for that kind of dependence. You don't tell the story about processes in space-time, and there's no intervening story. And I think what's characteristic about causal influences that there are interventions in the intervening, the modalities are different. There are interventions in the space-time that will break the connection, and that the modalities
right.
Are like that.
So that's what I think the interesting question about the weak values case is, because of course the whole you could say, well, it's not causal because I can't intervene here to bring this about.
Right.
But then someone might say, well, of course you can't, because this is in your future, right? You can't later do something to bring this about. And so, insofar as you took the interventionist story about causation, took that to be the right story about causation, that would be a reason for denying that this kind of dependence is a causal dependence.
Yeah, but instead of presupposing that there's no future past direct, I mean, this is how Hugh does it, right? You take the interventionist definition without making, and look at the counterfactual dependencies without making any sort of prejudgment about it. So that's why he gets that in the quantum case, there are ways of intervening on a future that would raise the probability of past ones. Therefore, he concludes there's past.
Yeah.
So
So one other thing I didn't mention on it, because you want to go away with something of value other than a bastardization of David Albert's views, whatever. So Laura is right to get me to talk about the interest of physics, and you can take something away. So let me just say one other thing about this for people who haven't seen it, because it's really cool. So one thought about this weak value stuff is it tells you there's something really important about time symmetry, right? That you had thought that quantum mechanics had this time asymmetry because of collapse. And so there's two things to say. One is notice that if you take a state preparation and a final state, and you take a sequence of projective measurements in between, and all you look at is the transition probabilities in between, then the whole picture is completely symmetric. That is, it doesn't matter if you take the final state, even if you've got a Hamiltonian, you know, if you reverse, like time reverse the Hamiltonian and apply it to a backwards evolving state, you get the transition probabilities coming out the same way as if you forward evolved. And then the other thing is to say, I think this is like really good if you've never seen it. Standard, you know, quantum mechanical interference. You imagine you've got detectors all the way along here, and you see the interference pattern by plotting the number of particles against the position of the detectors. But you get exactly the same interference pattern if you have a single detector at an arbitrary location, and then you vary the position of the source and plot the number of particles against the position of the source. So the people who believe in this sort of time symmetric approach think, look, there's like a lot more symmetry here. And I was thinking about this because of the Hugh Price thing, because people always say, you know, the retrocausality doesn't work because if I do some kind of interferometry thing, you know, I end up with it could come out here or here, but I know for sure that it went in there. And the objection to that is, no, you're just making the mistake of evaluating counterfactuals by holding the past fixed. But if you hold the future fixed, then you can say, well, it might have gone in there, you know. So the problem is that, like, it's really difficult to argue against that time symmetric way of thinking without illicitly putting in a kind of time asymmetric assumption into the way that you, or in this case, into the way you evaluate counterfactuals.
I think we maybe have time for just one more question.
Oh, okay.
He hasn't gone.
Oh, please, sorry.
I mean, what you said about action at a distance, you know, you made a distinction between action at a distance and non-locality, you know, referring to Albert.
Yeah.
That confusion might stem from the fact that it presumes certain classical notions of causality or spatial continuity that, you know, in which certain things are left out of the picture in action at a distance. You know, which the problem of action at a distance is what I'm saying is stems from the idea that certain things are left out of the picture in a macrocosmic situation. So if you change notions of spatial continuity, I would think that you would be left with a picture that would be more compatible with non-locality because of the symmetries and the fact that it kind of goes against certain notions of causality.
Right. Okay.
Maybe I wasn't clear.
I guess I'm not quite sure. I'm sure it's my fault for not understanding.
I'm just talking about space. Like if you replace macrocosmic spatial continuity with a different picture of space as maybe a discrete jump from one location to another, then it might adapt better to non-locality, and it would differentiate between that picture and action at a distance.
Yeah. I suppose if space is gappy, then by definition there's action at a distance.
If it's what?
Gappy.
If space is gappy, then there's by definition there's action at a distance, because you can't like find anything that transmits the effect from this point to this point in between, because there aren't any points of space in between. So that's an interesting thought. Like, on a discrete model of space-time, it has to be action at a distance.
Well, yeah, I guess I just meant that. I mean, if you start with a certain picture of space as continuous, then you get this idea of there being something missing in the classical picture, because something jumps mysteriously from one place to the other.
Yeah, but look, I mean, in these kinds of cases though, even if there was, like, space-time was gappy, I mean, it's not so gappy that there's nothing in between this wing of the apparatus and that wing of the apparatus, so you still have something weird going on over and above, like things jumping across the gaps in Planck scale lengths at which there's nothing in between. But anyway, I mean, the main thing I just wanted to say was I wanted to defend what I think of as a kind of orthodoxy that there's a kind of non-locality in quantum mechanics which is not as strong as action at distance. That's not, and that the term non-locality is misleadingly applied because it has all these connotations of causal action at a distance, and that we're not forced to that conclusion by the phenomenon. Anyway. You want to have the last word? Go on.
Sorry.
No, whatever you say, I'll just say something afterwards. Go ahead.